is the diagram that goes along with the problem. We can see that we have the ceiling here, and connected to it are two different wires. This one is angled 30 degrees from the ceiling. This one is 70 degrees from the ceiling. They meet together at this one wire, which is then connected to our modern sculpture, and together these wires hold up the sculpture. So the first part of the problem asks us to draw a force diagram with all the forces that are working in this diagram. It's important to realize that we need to analyze the forces that are acting on this point, which is where the wires meet and connect to the single wire, because if we were to look at the forces acting on this this point here, something like that, we would be counting the tensions as one whole, and we really need to see each of these individual tensions so that when we're analyzing them separately later, we'll have the distinction between the two. So for part A, we'll just kind of sketch what we have here. We have this same point with two tensions acting up. We'll call this T1, this T2, and then we also have mass times gravity pulling down at this point, which is the weight of this sculpture. So these are the forces acting on this point, but because later on we're going to need to use the x and y components of the two tensions, we should break that up now. So we can see here that if this is our y-axis and this is our x-axis, we're going to draw the coordinating components. So we're going to have, for each of the tensions, an x component and a y component. And when you're doing this, it's really important that you squiggle out the tension or something like that, so you can remember that when you eventually put it all together, that if you wrote all three of these directions, you'd be really counting the tension twice. So this reminds you that you're really only accounting for this tension one time, and same thing over here. So to break up this tension, we can do this off the side to make it a little bigger. We have this tension, which is T2. The degree measure at this angle is going to be 30 degrees, because we know from geometry that if this angle is 30 degrees, then this angle will also be 30 degrees. And then all we do is use trigonometry to solve for each of these two sides. So this y component will be opposite over hypotenuse, which is sine. So this will be T2 sine of 30 degrees. And this x component is adjacent to the angle, so this will be cosine. So you have T2, cosine of 30 degrees. Now we'll do the same exact thing over here with this tension. We call this T1. This angle measure is 70 degrees. Like we said, if this angle is 70 degrees, so is this. So this y component is opposite of the angle, so we're going to use sine because sine is opposite over hypotenuse. So that would be T1 sine 70 degrees. And then this one is adjacent to the angle, so we will use cosine. So T1 cosine of 70 degrees. So I rewrote and combined all the different forces that we just solved for. We had two forces that were acting in the positive y direction, so all we do is add them together. We had two forces acting in the x direction, but they were on opposite sides. This one was in the positive direction, and this one was in the y direction. And then finally we have the mass times gravity acting down on the sculpture. So for the second part of the problem, we want to find what the mass of this sculpture is if the maximum weight, or the maximum force that either of these two tensions can withhold is 2,000 newtons. So to do that, we want to use Newton's second rule, but we want to look at it acting in the y direction, because that is the direction that the sculpture is being held up in. So first we'll write Newton's second law in the y direction. So the sum of the forces in the y direction equal to the mass of the object times its acceleration. But in this case, the ideal is that the sculpture does not move, it stays stationary. So in that case, its acceleration would be 0. And if its acceleration is 0, then you're multiplying its mass times 0, And that means that this whole side of the equation is going to equal 0. So we know that we want the sum of the forces in the y direction to equal 0. So now all we have to do is substitute in the sum of the forces in the y direction. So in the positive y direction, we have t1 sine 70 degrees plus t2 sine 30 degrees. And we also have a force acting in the negative y direction, which is mg. And since it's in the negative direction, we'll subtract that value. So minus mg equals 0. Now, we're in a position where we can very easily solve for m because we know g, it's 9.8 meters per second squared, and we know one of the tensions. We know that one of the tensions can be 2,000 newtons. But we don't know the other, we only know one value for a tension, but we do know that these two tensions are different. So what we need to do is solve for a relationship between T1 and T2 so we can substitute that in and then use the 2,000 value for that tension. So that may be a little confusing, but let me show you what I'm going to do. We are going to use the forces acting in the x direction, and so we will say that the sum of the forces in the x direction equals mass times acceleration, Newton's second law. And the same thing applies here. We don't want our sculpture to be moving at all, which means the acceleration in the x and y direction would also be 0, which means that this whole side of the equation would equal 0. Now, all we have to do is substitute in our two different forces acting in the x direction, which would be positive t2 cosine 30 degrees. That value is acting in the positive direction. And then we want this value, which is acting in the negative direction, so we're going to subtract t1 cosine of 70 degrees. And together, those will equal 0. So we can now put these on opposite sides of the equation and set them equal to each other. T2 cosine 30 degrees equals T1 cosine 70 degrees. We can say here that we're solving for T1. So that means that that would be equal to T2 cosine of 30 degrees over cosine of 70 degrees. And if we do that, then that means that T1 is equal to 2.532 T2. So that means when we go back up to this equation, wherever we see a T1, we can just substitute that for 2.532 T2. So we'll erase this last part that we did here. So now what we're going to do is substitute this T1 value in for the value that we just solved for, 2.532 T2. So here we have our T1. So we'll write this as 2.532 times T2 times sine of 70 degrees plus T2 sine of 30 degrees, and then we'll say that that is equal to mg. We just added mg to the other side. Now we can substitute 2,000 newtons for T2 because we have just one tension. So we'll do that here. 2.532 times 2,000 newtons, put that in parentheses, put that in brackets, times sine of 70 degrees, plus T2 again is 2,000 newtons, times sine of 30 degrees, and that is equal to, altogether, mass times gravity, and we know that gravity is 9.8 meters per second squared times our mass. We solve for m, we find that m equals 587.613 kilograms. So, after all that, we have solved for the mass of this sculpture.